Hello, and I'm Mitko from Eindhoven University of Technology. So we moved to the session of novel extensions to convolutional networks. And the first talk is going to be, it's titled MIDL, Minimal Information Loss Dilated Networks for Gland Instant Segmentation in colon histopathology. And it's going to be given by Simon Graham. So, Simon.
So I'm a PhD student within the Tissue Image Analytics Lab at the University of Warwick, and today I'll be speaking about MIDL, so Minimal Information Loss Dilated Network for Gland Instant Segmentation. To outline the presentation, I will briefly introduce digital pathology, then I will go over the proposed method with the dataset and the results, and then finish off with a summary. So within routine pathology practice, a tissue biopsy is typically taken from the body. This is then cut into very thin sections using a microtome, and then most commonly, these tissue sections are stained with a hematoxylin and a eosin stain, where the hematoxylin binds to the DNA, staining that a purple-blue color, and the eosin stains the connective tissue and the cytoplasm a pinkish color. Then afterwards, this is mounted on a glass slide, and then traditionally, these slides are viewed under the microscope, whereas now there is a growing trend towards a digitized pathology workflow where these slides are scanned to obtain very high resolution images. And one of the advantages of this is the fact that we can extract information from these images automatically. And in particular, one application is the automated segmentation of glands. So this gland segmentation is a vital prerequisite step if we want to extract any kind of features from these glands. For example, the shape, the size, and textural features. So one example of what we can do, if we can segment the glands within the histology images, we've shown within our lab that we can then extract some morphological features, and these features can be indicative of the grade of colon cancer. However, even though this task is of importance, this remains a challenge because glands can be clustered together, and also glands vary in their shape and size, and therefore it can be hard to segment these glands. So here we have two images. On the left-hand side, we have glands that are clustered together, and on the right-hand side, with increasing grade of cancer, there is a lot of variation in the morphological appearance. However, current methods often follow an encoder-decoder approach, where these typically have downsampling for feature extraction and upsampling to localize the areas of interest. As well as this, skip connections are often used to transfer low-level information to the higher levels. But even though these methods have been very successful, they can be suboptimal for gland instant segmentation in particular. And this is because of the downsampling within the network that has a significant amount of information lost. As well as this, they often fail to incorporate the multiscale information, which is very important for gland instant segmentation. So to overcome these limitations, we introduce two custom residual units to counter the loss of information caused by max pooling. And as well as this, we employ Atrous spatial pyramid pooling to help aggregate multiscale information. So within typical CNNs, normally we have a combination of convolutional and max pooling operations. However, this max pooling operation can be destructive, and we lose a lot of the spatial information as we transcend through the network. And we hypothesize that this spatial information is actually crucial in terms of performing a superior segmentation. As we can see here, we have an example of a feature map, and if max pooling is performed, this can be destructive, and only the highest activations within each bin are sent across to the next level. So we propose two additional residual units, additional to the traditional residual units that were proposed in 2015. So within the traditional residual unit, the feature maps are input into the residual unit, and skip connections are used for a superior performance. However, we use minimal information loss residual units, and the idea here is that we downsample the original image, and then we feed this through a convolutional operator, and then we concatenate this with the feature map, and then this concatenated feature map is used in the summation operation as opposed to just the feature map itself in the traditional residual unit, and therefore this helps to alleviate the loss of information caused by downsampling. As well as this, we use dilated convolution within the residual unit, and the idea here is that instead of using just standard convolution, we use dilated convolution, and here instead of the need for downsampling to increase the size of the receptive field, we can introduce sparsity within the kernel, and therefore we can increase the size of the receptive field this way without the need to downsample and lose the spatial information. Then this combination of the MIL units and the dilated residual units can help to reduce this amount of spatial information that is lost, and therefore it negates the need to introduce additional cues to perform instance segmentation. For Atrous spatial pyramid pooling, this is mainly used to aggregate multi-scale information, so therefore it performs a successful segmentation for glands of varying size. Specifically, this is the makeup of the Atrous spatial pyramid pooling module, where we aggregate dilated convolution with dilation of rates 6, 12, and 18. We concatenate this with a 1-by-1 convolution and also global average pooling. And the reason why we use global average pooling is because when the dilation rate is too large, there are redundant convolutions, and therefore this boils down to a 1-by-1 convolution. Then when we concatenate all this together, this gives an effective multi-scale unit. So we combine the minimal information loss feature extraction network with the Atrous spatial pyramid pooling network to give an effective feature extractor overall. So note we have the MIL units only after the max pooling operation, because the aim here is to help alleviate the loss of information caused by max pooling. Then after this feature extraction, we upsample in a typical UNet style fashion, where we output the object and also the console. However, we only use the object in terms of making the prediction, and we use the console to refine an uncertainty map that is generated in the slides to come. So in terms of uncertainty map generation, we use a technique called random transformation sampling, and the idea here is, given a test image X, we can generate a sample of augmented images. So we choose to perform random flip, rotation, blur, and also Gaussian noise. And here we can obtain a sample of transformed images. And then we pass all of these images through the MIDL. And then afterwards, we can take the mean to obtain a refined prediction and the variance to obtain the uncertainty. So a bit more clearly, we have a sample of transformed images that are sent through the network to obtain a process sample, and then the mean will give us the prediction, and then the variance will give us the uncertainty. Then what we want to do here is to define an uncertainty score to help disregard predictions with high uncertainty. So given an original image, we can obtain the uncertainty map via random transformation sampling, and how we use the console is we choose to subtract the contour from this uncertainty map. And this is because within the uncertainty map, there are areas of high uncertainty around the boundary, and that is a given because as we go between two classes, there are areas of uncertainty that can't be avoided. And so therefore, to give a more refined uncertainty map, we choose to take away the contour. So with this refined uncertainty map, we give an instance level uncertainty score. So for each prediction that's been output by the network, we associate an uncertainty score for each prediction. And this is done by looking at the output, so the binary output, and then the associated contour removed uncertainty map, and we take the mean value within that uncertainty map. And then the idea is we can disregard those instances with a high uncertainty score. Now, in terms of the data set we use two independent colorectal adenocarcinoma datasets. The first one, as I'm sure many of you have heard of, is the Glas Challenge dataset, where we have 85 training images, 80 test images, and are mainly of size 775 by 522. And the second dataset is a colorectal adenocarcinoma gland dataset that we call the CRAG dataset, where we have 173 training images, 40 test images, and a much larger of size around 1512 by 1516. And we plan to put this into the public domain in some time in the future. So a bit more clearly, we have some images from the Glas dataset at the top and the CRAG dataset at the bottom, where the yellow contours highlight the glands, the black boxes show some areas where the glands are clustered together, and all are H&E stained and 20 times magnification. Now this shows some of the results in the Glas dataset. So there were a lot of entries for the Glas challenge, so we can't fit them all on the slide. But the decant method was the winning submission to the competition, and we also choose to show some entries that have been published after the competition. So we can see here that on all statistical measures, F1 object Dyson object Hausdorff, we achieve state-of-the-art performance. Some examples. We can see here that our method performs superiorly in terms of instant segmentation, and we have very smooth glandular boundaries. For the CRAG dataset, we choose to compare with some of the current methods, and we also achieve state-of-the-art performance significantly. Now this dataset is a lot more tricky. So there's a lot of instances where they're very hard to segment, but our method does a very good job in achieving gland instant segmentation and looks very similar to the ground truth, whereas a lot of the other methods fail to make a successful segmentation. For random transformation sampling, we see that using that refined prediction leads to a significant improvement in the performance on nearly all the measurements, whereas the F1 score just remains the same. So therefore, this idea of random transformation sampling actually does increase the performance. Then these graphs here show the effect of disregarding predictions with a high uncertainty. So we can see here 3 graphs, where on the x-axis we have tau, and tau represents the threshold that is used to disregard predictions with a high uncertainty. For example, if you have tau as 4, this means that any instance with an uncertainty score greater than 4, we will disregard. So it makes sense that the higher the uncertainty score, the more glands remaining within the data set, but it won't be as destructive in terms of removing those glands. And then if we have an uncertainty score around 1, we are still able to keep a significant amount of these glands within the data set, but we can also significantly increase the performance. So to conclude, we presented a minimal information loss dilated network for gland instant segmentation, where we reduced the loss of information caused by max pooling by introducing 2 additional residual units, and we also aggregated multi-scale information by using Atrous spatial pyramid pooling. We incorporated uncertainty via random transformation sampling and achieved state-of-the-art performance on 2 independent colorectal adenocarcinoma datasets. So I'd like to thank all the members of the Tissue Image Analytics Lab, especially my supervisor, Nasir Rajput. Thank you to the conference organisers, my university, the University of Warwick, and our collaborators at Chinese University of Hong Kong, and especially thank you to the funders, EPSRC and MRC. And on a final note, the European Congress on Digital Pathology will be at Warwick in 2019, and so we'd love to see as many of you as possible there. Thank you.
Thanks, Simon. Are there any questions?
Hey, so you make this claim on the minimal information loss layer being useful. Do you have any study specifically confirming that or the different components of the network?
So we didn't do any significant ablation study, and the reason why we didn't do that, one was obviously time, but second is the fact that there are so many entries and so many published methods for the Glas challenge dataset especially, and so the only real difference is the fact that we've included this minimal information loss unit and also the combination of this with the dilated residual unit. And so we hypothesize that it's this combination of residual units that leads to the increase in performance.
Other questions?
Hi, thanks for your talk. I was interested in the sort of the test time data augmentation
Yeah.
and this uncertainty term. To me, it seems like the uncertainty might be capturing the inability of the network to model invariances to certain
Yeah, sure.
transformations. Is that basically what it's doing? Because for me, that
Essentially, yeah. So I guess what we were trying to capture was the perturbation in the input space. So we're looking to see what happened. We're trying to gauge the predictive distribution corresponding to these perturbations. So whether that's the augmentations, within the images. So I guess that's exactly what is trying to be captured. Yeah.
Okay, thank you.
How much data augmentation was used during training the network? So did the network see these augmentations before?
Yeah, so they did see the augmentations, but obviously, so during training of the network, we applied augmentation, but these augmentations that were performed at test time were random. So even though we performed the augmentation during training, it may not have seen all possible configurations of the augmentation. And so maybe it saw some examples that it would not have seen during training.
Okay, let's thank the speaker again.